Okay, let's wait for maybe 1 or 2 more minutes and we'll start. Okay, it's the time, so let's get started. Hi everyone, thank you so much for joining us. And so today, we'll have the first webinar, the BNP webinar for this academic year. Like the last year, we will have 4 webinars throughout the year. And so you can check the full schedule from our BNP website. And our first speaker is Guillaume KonKamKing from INRAE in France, and he will talk about Bayesian nonparametric mixture models and the posterior number of clusters. He has one correction, minor correction in his abstract. I guess he will talk about it maybe at the end of the talk or so. So yeah, let's welcome the Guillaume.
Thank you very much. Thank you, Julie, for the invitation, and thank you for coming. I see many familiar names connected, so I'm happy to present this work to you. I'm going to speak about Bayesian nonparametric mixture models and look at the posterior number of clusters, or estimating the number of clusters. This work is mostly extracted from the PhD thesis of Louise Alamichel, who defended in Snow at Bocconi. And also parts of it can be found also in Caroline Lawless' PhD thesis. And this is joint work with Julien Arbel and Daria Bistrava. So let me first start by introducing mixture models and see that would be the occasion to state some notation. So a mixture model is composed of a latent mixing measure that I'm going to call G, then a kernel. And so the mixture density involves mixing the kernels with the mixing measure. So K can be, in this notation, finite, and that would be a finite mixture, or infinite. And in this case, there would be an infinite mixture model. And below, you have a figure where you can see each of the components. So the components, they have they have a location that is determining the parameters. So you can see them in colors, and the mixing measure involves these atoms and the weights. So the weights here of each component are not represented, but they are taken into account in drawing the mixture density in black. And so mixture models are extremely popular. There's a variety of reasons for this. One is that if you don't believe in your assumption of population homogeneity and you want to have a more complex or flexible model, the first step you can do is assume a mixture model. They are also used for model-based clustering. They provide flexible density estimation tools. And they are especially popular because they offer good interpretability. The various mixture components often have a meaning when you try to apply them. And so that's why you see applications in many fields, genetics, ecology, epidemiology, etc. And if you're interested in some statistics archaeology, you can even find online the data for one of the first uses of mixture models from Carl Pearson, who had some data about crops and fitted the 2-component mixture models using moment matching. And we are interested in the the case where you don't exactly know how many components there are in your mixture. So in the model-based clustering framework, so here you have the notation that I introduced just before, data, a latent mixing measure, and the mixture density. And there's an equivalent hierarchical representation using allocation variables Z1 to n. So for each of the data points, you have a discrete random variable Zi, which tells you what components the data point comes from. And of course, when you have the weights of the latent mixing measure, you can come from any of the components with a probability equal to the weight of the mixture measure. These allocation variables, they define a random partition of your of the n first integers, a random partition of your data. And this random partition can, because Z is a random variable, it can contain Kn clusters, okay? And so Kn is also a random variable in this model. So there's an important distinction that was highlighted in papers by Sylvia Frovier-Schnatter, but also many others, between components and clusters in the mixture model. So here you have the same picture as before, except that now we have some data points that are sampled, and the color of the data points corresponds to the allocation variable, to which mixture they come from. And so you see that we have data points coming from 3 components, and we have no data points coming from the yellow and this gray component. And so we call K the number of components in the mixture model. So here it could be 5 or more because maybe I haven't drawn all the components. And Kn, the number of clusters in the data. So the number of components from which you actually observed a point. And clearly, Kn is smaller or equal to K. And now let's consider two questions that are usually addressed using mixture models. And the two questions might look the same, but there's some subtle difference between the two that we're going to see. So the first question is a typical applied question. So you have data generated from a mixture model with K components, and you want to infer the number of clusters in your data. So to reformulate this question is how many clusters do I have in my dataset? Another similar question, but not exactly the same, would be so you have data that comes from a mixture model with K0 components, and now you're interested to learn about this K0. So this type of question could be reformulated as I have a population which might be infinite. I can gather some data on this population. And the question is, what's the latent structure of this infinite population? Okay, what is K0 independently of my given dataset? And so some classical tools that deal with these questions are the following. So first, finite mixtures. So we consider K finite. There's the approach where you fit many models with different values of K, and you select the best one according to some criterion, BIC, AIC, or something. And this I classify more as the second type of question, where you try to learn the K0 in your model, in your population. There can be some debate about this, but at least that's the type of guarantees that AIC provide you. Asymptotic guarantee that you recover a true number of clusters. So if you use these tools, probably you somehow believe in this kind of framework. So another use of finite mixtures would be overfitted mixtures. So for instance, they've been discussed in this article by Judith Rousseau and Kerry Mangersen, where you fit a mixture with K larger than K0. You know that your mixture has more components. And then you look at Kn, the posterior distribution on the number of clusters in your data. And this is more like the first type. You're not aiming to find K0 because, I mean, K0 does not correspond to a parameter in your model. Okay. So you're more trying to look at what you have in your data. And there's also some other types of models, which are mixtures of finite mixtures. So in this case, you place a prior on K, and you can look at, or you try to perform inference on K0 by looking at the posterior distribution of K. And so you can find some examples here in this reference. But you could also look at the posterior distribution of Kn. So actually, with this type of models, you would be able to sort of address the two types of questions. And then you have infinite mixture models where you set K to infinity and you look at the posterior distribution of Kn. In this case, you're certainly, you don't have a K0 in your model. Okay, so it falls more in the category of how many clusters do I have in my data? So you have these different approaches and a typical evaluation framework, which has been used in many previous publications, is the following. So for each of these methods, I take a data generation mechanism, which is I take some data generated from a finite mixture model with K0 components. And then I consider Kn, the number of clusters in the data, as an estimator of K0. And the next question is what's the asymptotic behavior of Kn as the sample size grows to infinity? And more precisely, those Kn converges to K0 as n grows to infinity. And so this framework has been discussed, maybe presented as not appropriate in the sense that it mixes a bit the two types of questions. Okay, you use this framework to evaluate some priors or some models which are geared towards this type of question, whereas the evaluation framework is more about finding K0. But we can find some sort of justifications for this evaluation framework. One is a typical frequentist justification to say, among all these methods, if I have a population with a fixed underlying structure, and I can sample from that population repeatedly, among all these procedures, then I'm going to retain only procedures that have the minimal requirement of recovering the underlying structure with enough data. Okay, that's we want the asymptotic properties of the method to at least be correct. It's not a guarantee that it's going to be efficient, but it's more like a minimal logical requirement. Another possible justification for using this type of evaluation framework, here I'm quoting Judith Rousseau on this, is that when you study the asymptotic behavior of your model or the asymptotic behavior of Kn for our favorite models, you understand some mechanism, you understand better how they work, and you get some additional insights on this. And we'll see that we get some insights about how our Bayesian non-parametric model works. I'm giving a quick overview of existing consistency results. And so here I'm showing the quantity of interest. So if your interest is trying to recover the density, or if you're trying to perform density estimation, then there's a bunch of proofs of consistency for all of the three approaches: finite mixtures, infinite mixtures of finite mixtures. So some have been summarized in the book of Sylvia Freuwert-Schnatter about, with Christian Aubert and Gilles Seleux about mixture models. If your interest is the latent mixing measure, there's also some positive consistency results due to Nat Ho and Swanlong and Guillaume, and also in the case of mixture of finite mixtures by Nobile. And now, if your interest is recovering K0, the number of components in your data generating mechanism, so there's no question where K is fixed. In the case of other 15 mixtures, we get some negative and positive results that I'm going to discuss. In the case of infinite mixtures, there was this early results by Miller and Harrison. There's also an extension to, so this one for Dirichlet process and generalization to Pitmanian processes, which give negative results on the consistency to estimate K0. And here I forgot to add some gray, but we extend these results to more general Bayesian nonparametric processes. And for mixture of finite mixtures models, you have positive consistency results by Guha, Ho, and Guillaume. So negative, but we'll see also some positive results. Positive results by Ascolani, Lioi, Rebaudo, and Zanella, and also some sort of positive results by Guha et al. So this is the reference that I that I mistook in the summary. This was the correct reference that I wanted to use. Okay. And so the outline of my presentation today will be a first part where I speak about the posterior number of clusters. I'm going to detail the existing, or to summarize the existing inconsistency results, show how they can be extended to Gibbs-type processes and multinomial processes, and then explore the strategy by Ascolani and colleagues of putting a hyperprior on the parameters and see if this can restore consistency. Then in the second part, I'm going to change a bit the perspective and look at the latent structure and discuss how this can be used to recover the K0, the number of components. And so let's start with a more precise statement of the context. So a priori, we know that for both finite and infinite mixtures, when the sample size grows to infinity, the number of clusters converges almost surely to K. So if it's a finite mixture and you get an infinite sample size, after a while you have got samples from all of your components. And if it's an infinite mixture, the number of clusters in your data grows indefinitely. And this is an argument, for instance, made in this article by Rafael Argento and Maria De Iorio. And now the question is, what happens a posteriori? So is the data enough to introduce a different behavior for the number of clusters? So here we look at, we consider the asymptotic behavior of Kn, the number of clusters in the data, when the data is generated from a mixture with K0 components. And in this context, posterior consistency for the number of clusters is defined as in this way, it means that the probability that the posterior number of clusters is equal to K0 goes to 1. And the results by Miller and Harrison in these two publications show that you have inconsistency. So in this, in the same setting, so the data coming from a finite mixture, if you fit a Dirichlet process mixture or Pitmanian process mixture, and you look at the posterior number of Kn, under some mild assumptions on the component family and the prior and hyperparameters, you have these inconsistency results. And the structure of the proof involves two main ingredients. I'm simplifying a lot here, but there's one condition on prior partition control. So it's a bound on the ratio of prior partition probabilities when considering two partitions, any given partition and the new partition when you take one of the data points and you create a singleton. And then there's another condition based on the likelihood, which is a mild condition on single cluster marginals, which holds for many common kernels. So for instance, all of those in the exponential family. And so let's examine a little closer this first condition, the partition ratio. So we consider AKN, the set of partitions with K elements. Okay. Now, for any elements of this AKN, we consider the new partition BAG, which is obtained by, as I mentioned before, taking a point out and creating a singleton. Okay, so of course, you can't take something that is already a singleton to create a new one. So there's some details that I'm skipping over, but basically, I'm considering this type of new partitions. And these are all collected into a set ZA. So the the condition that I mean, this condition one in Miller and Harrison is that the the maximum of this ratio for all the partition in AK and all the partitions B in this set, so all the with the new singletons, um, must be bounded. Okay, this is this condition. And Miller and Harrison show that this condition is verified for the Dirichlet process and the Pitmanian process. We will show that they also hold for Gibbs-type processes in the next slides and also multinomial processes. So before I start describing this, let me remind or describe the type of processes we consider here. And so Gibbs-type processes, they are a very rich class of Bayesian nonparametric processes, which include the Dirichlet process, the Pitmanian process, and also, for instance, the normalized generalized gamma process. And part of the characterization is that the probability, the prior probability for this for a partition, so we call this the exchangeable partition probability function, takes this form where you have one discount parameter, sigma, which is smaller than 1, and then weights V and K appearing here, which follow a specific type of recursive relation. And so you get to the Dirichlet process by setting sigma equal to 0 and having this type of weights. You can also get the Pitmanian process or more general versions. Now, let me introduce multinomial processes. And this is important because, I mean, this is interesting because it shows that this, let me rephrase. So you might had the preconception that this inconsistency result of Miller and Harrison would hold in infinite mixture process because a priori you have an infinite number of components. And so this is a very strong prior information. But one of the surprises that we had was that you get exactly the same type of inconsistency results for finite mixtures. So even though the prior information might appear less strong, you have the same behavior posterior. And so we turn to a specific type of finite mixtures, which are very interesting for many reasons, which are the multinomial processes. So they were introduced by Thomas Oregon, Antonio Lioy, and Igor Prünster in Thomas Oregon's PhD thesis. Here I'm presenting them in a hierarchical form because that's what makes them most familiar, but there are many ways to look at them. And so, for instance, you get the Dirichlet multinomial process if you consider something very much like a Dirichlet process mixture, but instead of using a diffuse Bayes measure, you use a finite, a discrete mixture, a discrete measure as the Bayes measure. And in this case, instead of having the infinite mixture like the Dirichlet process, you can only sample atoms from this Bayes measure, and so you get a finite dimensional mixture. And so it's also very elegant because you can construct Dirichlet multinomial processes, but also Pitmanian multinomial processes, or even a more general class of multinomial processes called the normalized infinitely divisible multinomial processes, which is let's say the finite dimensional counterpart of normalized random NRMIs. And this is the relation between BNP processes and the corresponding multinomial processes. So Gibbs type priors, you see that they include those two. And I mean, you can move from one type of one process to another using a type of multinomialization idea. And so the multinomial processes are interesting because they are flexible finite dimensional priors. They have closed form posterior characterizations. And so you can build exact sampling algorithms. They converge to their infinite dimensional counterparts as k grows to infinity, which means that some of the intuition you have on your favorite BNP processes, you can also translate for the multinomial versions. Especially, for instance, the interpretation of the parameters, for instance, the fact that alpha will have an impact on the posterior number of clusters or prior number of clusters. This is also true for these multinomial processes. And you can find examples of application in these papers. And so we extended the results of Miller and Harrison to these two families of processes. The condition 4 in Miller and Harrison holds without problem in these cases. And so the question here is to examine condition 1 in these two contexts. And so the results that we got was that for Gibbs type processes, condition 1 also holds for any fixed k. Also for Dirichlet multinomial process, Pitman multinomial process, and normalized generalized gamma multinomial process, condition 1 also holds. Note that we were not able to prove that condition 1 applies for normalized infinitely divisible multinomial processes. So there might be something different going here. This we don't know exactly. So to prove this condition 1 for Gibbs type processes, the strategy is that so we want to bound this C and K, which was the maximum of the ratio of these probabilities a priori. And so we can bound all of these probabilities. And in the context of Gibbs type processes, this reduces to bounding the ratio of the weights that come in the ePPF of Gibbs type processes. So this can be done using the recursion relation of the V and K. And also, since there's no analytical formula, where we used the Laplace approximation for these V and Ks that were developed by Julien Arbel and Stefano Favaro in another publication. For the multinomial processes, the ePPF is available in closed forms. It involves finite sums, thanks to the work in these papers. And so you need a slightly different proof in each of the cases, but in general, the idea of the proof is to rearrange the sum, perform them in a specific orders, and then use some recursive relation for the generalized factorial coefficients that appear in the ePPF. And so here I'm giving a visual illustration of the results that we got, where here you have n increasing, then the ratio that you need to bound to satisfy condition 1. And this is the evolution of the ratio as a function of n for different values of k. And you see indeed that for all of these processes, it remains bounded as k increases. So this is just a visualization of some specific parts of the results. And we also examine the simulation scenario of these results. So we consider the very simple case of a Dirichlet multinomial process. So it's the type of mixture, and it's very similar to the type of mixture you would use, or let's say a vanilla type of mixture model, where you have a Dirichlet prior for weights, only with certain parameters. Okay. We look at the prior number of clusters and the posterior number of clusters in a simulation scenario where the K0 is equal to 3 and we have fairly well separated components. So given the variance here, all of the components are far apart. And so in dashed lines, you see how the prior number of clusters evolves as the sample size increases. And as expected, the prior number of clusters concentrates on k equal to 10. Sorry, I forgot to say that I'm using a Dirichlet multinomial process with k equal to 10. So a priori, the number of clusters concentrates towards 10. And you see that a posteriori, you also have consistency where the posterior number of clusters moves away from 3, which was the value of k0. And so in this simple case, we could see the inconsistency. But there was an elegant Bayesian solution to the inconsistency problem, which was proposed by Filippo Ascolani, Antonio Lioi, Giovanni Rebaudo, and Giacomo Zanella, which was to put a hyperprior on the alpha, the concentration parameter, in the case of the Dirichlet process mixtures. So here you have a typical Dirichlet process specification, and here you have the hyperprior on alpha. So the result requires some conditions on the prior distribution, but which are typically satisfied by gamma priors, so fairly natural prior for alpha. Then there are conditions on the kernel. So this is slightly more unusual because the kernel needs to have bounded support. So they have to be 0 everywhere except on a bounded interval. And there's so some condition on the base measure, and also an assumption that the true components are completely separable. So there's no overlap between the mixture components. But in this case, they were able to show that you recover posterior consistency. So Kn concentrates on the true number of components, and you can also they also looked at the posterior distribution on alpha, and it concentrates on 0. So that should make things more reasonable when you think about how the number of clusters in a Dirichlet process depends on this parameter. So we were curious to look at whether this strategy can extend to the Pitmanier process. And we first started by then using the same setting, but replacing the Dirichlet process by a Pitmanier process, fixing the discount parameter sigma, and then using the same type of priors on the alpha parameter. And the result of this investigation was that under the same assumption as Colony et al., you don't have consistency for the number of clusters here. And this was in the case where data comes from a single component mixture. So let's try to see what's going on here. So the idea of the proof is that to get consistency, it's it's equivalent to look at this sum, which involves the ratio of the posterior probability of the number of clusters being equal to S for all possible values, compared to the posterior probability of having a single one cluster. And posterior consistency requires that this goes to 0. And so we got inconsistency just by showing that one of the terms in this sum doesn't go to 0 as n goes to infinity. And so, for instance, you can pick the posterior probability of Kn being equal to 2. And if you write this, you can separate this ratio into 2 terms, where the first one doesn't go to 0, and the second one is bounded below by a constant, and so it cannot go to 0. This in the paper with Caroline With Caroline Lawless, we explored with k equal to 1, but there's a generalization and in Louise Alamichel's PhD thesis with weaker hypothesis and any sorry, data generating mechanism with any values for k0. And just as a remark, I mean, in Ascolani and colleagues, they used exactly this, I mean, this same type of decomposition, but in their case, the first part, which which was specific to the Dirichlet process, was going to 0. So the difference here is that the addition of the discount parameter prevents prevented this term from going to 0. So there's something, I mean, something in the ePPF is playing a strong role. So let's look at simulations in this case. So it's the same simulation setting as before, k0 equal to 3, fairly well separated components. And then we look at the posterior distribution on Kn when we increase the sample size, and we see no concentration, actually quite the opposite. We were also curious, but not able to prove, to get results here, but we were also curious to investigate what happens if you fix alpha and maybe put a prior on the discount parameter of the Pitmanian process. And in this case, this was quite a surprise. It seems that the approach was quite consistent. Take this simulation results with a grain of salt because the MC convergence was a bit challenging, and so it might be that if we were not certain that there is consistency in this case. And the last thing to try was to put a hyper prior on on both parameters. And in this case, I mean, the simulation seemed to indicate that there was no consistency. Okay, the posterior number of clusters is going away from K0. And so there's definitely more exploration to be done about this, but it's also interesting to do a change of perspective and consider the latent mixing measure. This is because there were some positive results about the posterior behavior of the mixing measure. So what we are going to do here is to look at the posterior distribution of the mixing measure and see if we can infer the number of components using this. And so, for instance, work by Nguyen and colleagues show that the latent mixing measure converges to the true mixing measure in the Wasserstein metric in finite or infinite mixtures. So in the Wasserstein metric, it means that the atoms end at the correct location and with the correct weight. Okay. So note that the convergence of the latent mixing measure to G0 in the Wasserstein metric does not imply that the posterior number of clusters, or it's not incompatible with the fact that the posterior number of clusters would go to K0. Because even if you have components with vanishing weight, if you let sample size go to infinity, there's a chance that you might get a sample from a component with vanishing weight. So these two types of results are not incompatible between them. But the hope is that we may be able to read K0 from the posterior distribution of G. And indeed, that's one of the insights that come from work by Judith Rousseau and Kerry Mangerson on overfitted mixture models. So they were studying overfitted mixture models when K is larger than K0 and found that when data is generated from a mixture model with K0 components under mild conditions on the component family and the prior and the weights, the posterior distribution concentrates on configuration where extra components are emptied or merged with true components. So let's see a little more closely this type of results. There are various conditions, but one condition that is interesting is a condition on the prior of the mixture weights. So the prior on the mixture weights in the Rousseau and Mangerson framework should involve polynomials in the weights and is multiplied by a C function that is bounded from above and below on the simplex. And so with some further conditions on the kernel, they found that there are two asymptotic regimes as n goes to infinity, a phase transition in a sense. So if the largest alpha parameter, here you can allow the alpha parameter to differ in the weights. If the largest is smaller than d over 2, then the weights of extra components, the k that are superfluous with respect to k0, will go to 0. And in the opposite case, if the smallest alpha is larger than d over 2, where d is the dimension of the data in the mixture model, then the extra components are merged with true components. So this means that you will find two components with almost the same location, and they share the weight of the original mixing measure. So this is what is meant when we say merging. And so if you get this type of result in practice, what you would be tempted to do would be, if you are in this case, so the weight of the extra components go to 0, you could trim all the small weights below a threshold, and this threshold goes to 0 as n goes to infinity. So you can take a smaller and smaller threshold if you have a large sample size. Or if you are in the other regime, where you have merging of components, then if you have a posterior distribution, you just merge together the components which are almost at the same location. You sum the weights, and then this should give you a way of estimating the K0. And so we were curious to see if this result on overfitted mixtures applied to the interesting multinomial processes. And so for the Dirichlet multinomial process, it's fairly easy to see that the framework of Rousseau and Mangerson apply, because here you can readily recognize the Dirichlet density, where this would be a constant. And so if you do a simulation from a Dirichlet multinomial process, still the same simulation framework as before, you can see, so this here is the weights of the posterior distribution on the weights when the weights have been sorted sorted in decreasing order. And so the posterior distribution on the largest weights, second largest weight, etc., etc. And then we increase the sample size, and we see that as the sample size becomes large enough, since K0 is equal to 3, we have 3 weights that are decidedly different from 0, and the remaining weights start to have start to vanish. This is what you expect when you have alpha equal to 1 in this case. And so we look at whether these positive results on overfitted mixtures could be could apply to the Pitman multinomial process, for instance. But it's actually not telling us much, because the prior on the weights, distribution on the density on the weights is not explicit in most cases. And even for the Pitman process with Pitman multinomial process with sigma equal to 1/2, where a prior density for the weights exists, you can find no parameterization such that the condition is satisfied. So it turns out that unfortunately this Rousseau and Mangerson framework for overfitted mixtures is not able to tell us anything for this Pitman multinomial process, and probably other multinomial processes as well. And so let's explore a different approach. which was developed by Xuanlong and Nguyen and colleagues in this paper, where you would do exactly what you expect, given that you have the convergence of the latent mixing measure to the true mixing measure. You would merge some components, truncate some other components, and maybe merge them. So Guo and colleagues introduced this algorithm and were able to show that this algorithm, which is a post-processing of the posterior distribution, gives you allows to produce a consistent estimate for K0. So the setting is again data generated from a finite mixture model with K0 components. Then you consider GI, one posterior sample from the latent mixing measure. And so if you have a Bayesian procedure such that um, you have convergence in the Wasserstein metric with a known rate, then you apply the MTM algorithm to your posterior samples, and it will produce consistent estimates of K0 and also of the mixing measure G0. Let me describe you with pictures this merge, truncate, merge algorithm. So the first step, you suppose that you know a convergence rate and the Wasserstein metric for your mixing measure. Here in gray, you have one posterior sample. So gray is just one mixing measure, which is a sample from the posterior. And the first step of this merge truncate merge algorithm is to merge atoms which are closer than omega n, okay, which is given from the rate of convergence. So you draw I mean, you consider all the atoms in your mixing measure, and if they are small, closer than this threshold, you put them together and sum the weights. The second step is truncation, where after this merge, you look at atoms which have a mass lower than a certain threshold, and the threshold depends on the convergence rate, some constant C that is unspecified, and also the type of Wasserstein distance that you are considering. And so using this threshold, you perform a truncation. And then there's a last merging step where you merge again atoms that are closer than a threshold. And so if you apply these three steps, merge, truncate, and merge, then they were able to prove that you get, I mean, the output of, well, the post-processing of your mixing measure sample can be denoted G tilde. And then the number of components in G tilde converges to K0 with the probability 1. And so Gua and colleagues show that this was a consistent procedure for the Dirichlet process mixtures. And we tried to see if this could be extended also to the Pitman process and overfitting mixtures, which would include the multinomial processes. And so we were able to extend it to the Pitman process, where considering results from Katia Scricciolo, we were able to deduce a convergence rate for the mixing measure in the special case of a univariate location mixture with known scale. And so that's maybe a pretty restrictive context, but in this case, I mean, it shows the potential for this merge, truncate merge algorithm to obtain consistent estimates. And in the case of overfitting mixtures, it was also it was possible to combine various results of Xuanlong and Guillaume to prove consistency of this MTM algorithm. And this is a simulation study of the MTM algorithm applied to posterior samples. And it was interesting to explore this by simulation because, as I mentioned, there's a constant C that is unspecified. And this constancy is involved in the truncation step. So depending on which value of C you choose, you get a different answer because you don't truncate the same components. And so what we did here was to change the value of C. So here you have increasing values of C. Then we apply the post-processing to many posterior samples, and we look at the mean the mean a posteriori for the K tilde estimator or the maximum a posteriori for K tilde. And we saw that as you start having larger samples, you get a certain robustness to the value of C. So if you take C very small, you don't truncate much, and then your estimator gives you a lot of clusters. And then if you increase C, you reach a plateau here that is exactly at the right value. And then if you keep increasing C, there's a moment where you truncate every clusters, and then you get your estimate equal to 0 or to 1. I mean, it doesn't make much sense. So this suggests a heuristic method to choose C, which is that you should try certain values, and hopefully, if you see a plateau like this, it means that this would be your. I mean, this is the estimator that you should choose. It's just a heuristic, but it was. I mean, it's still interesting to explore this MTM algorithm. So I'm wrapping up now. The overview of the existing consistency result gives some positive and negative results for overfitted mixtures and infinite dimensional mixtures. So if you look directly at K, the posterior distribution on Kn, you have inconsistency in this specific asymptotic framework, but you have some consistent post-processing methods. And here, of course, you can look at this and see, why don't I use mixtures of finite mixtures all the time? Because they seem to be consistent in every cases. And I think this is a slightly misleading picture because this is the asymptotic framework that we gave ourselves, where data comes from a finite mixture. But in the case of mixture of finite mixtures, we lose the very desirable property of typical BNP frameworks, typical BNP priors, where the number of clusters is going to grow with the size of your data set. Or let's say you can use the same prior for different data set size, because your model automatically adapts the complexity to the amount of data you have. And this is a very desirable framework. And in my understanding, in most applications, when you have more data, you expect to see more complex latent structures. There were a couple of related works that I did not discuss in this presentation. A big body of work is loss-based Bayesian estimators, which show good empirical performance. So for instance, if you look at your posterior on on the space of clusterings and try to find the estimator that minimized the variation of the information loss function or other versions, uh, you you, you get a good empirical performance. This has been explored in work by Sarah Wade and David Dunn, notably. But the theoretical analysis of these loss-based Bayesian estimators is fairly difficult. I've tried a couple of times with Julien and didn't make much progress. There are some results by Chambaz and Rousseau, which look at consistency for the map of the number of clusters in finite 1D mixtures, but this is a fairly restricted framework. There's been some exploration by Lukas Raskowski, who looked at the map partition in Dirichlet process mixtures and got some good results, but some negative results. So it's hard to get to the end of it. And if you're interested in these questions, you can look at some exploration by Louise Alamichel and Filippo Ascolani in Louis' PhD thesis, or also the PhD thesis of Caroline Lawless also has some exploration of this. There are also priors which changes with n. So for instance, a Dirichlet process mixture where you let alpha decrease when n increases. And so work by On and Lin and also Zhang and colleagues, Leo Dion, show that these were produced consistent estimators. Large amount of work, which looks very interesting about repulsive mixture. You expect a very different behavior about the posterior number of clusters in repulsive mixtures. So I've just quoted a few papers about this. An interesting different asymptotic framework that was explored by Michael Jordan and several colleagues, where instead of having data which is generated from a single, from a finite mixtures, finite K0, you have a number of clusters that grow with n. So this was explored, but it's still preprint. There's, it's not finalized work yet. And then I will just skip over this, but if you consider now misspecified mixture models, you have very different stories about the number of clusters. Thank you for your attention. If you want further details, don't hesitate to look at these two resources. And otherwise, I'm happy to take any question.
Thank you, Guillaume. And it's very nice talk. And now we have about 5 minutes for the Q&A. Please raise your hand if you have any questions.
I have a quick question.
Mhm.
Guillaume, very, very nice talk. I would like you to speak a little bit about this idea of the components being completely separable. What does that look like in practice? Could you give a little bit more detail? It seems like that's a key component to any of the results. At least some of the stuff that you talked about. What are some of the mathematical details there? What does that look like in practice as completely separable components?
And so this was necessary for the priors, the result with the hyper priors on alpha. And the intuition is that the components in the data generating mechanism do not overlap. So you have components that, or let's say, you have data that is generated from a two-component mixture. We have kernels with finite support, and their support do not overlap. So if you have one point, you can say which cluster it comes from. Okay, it's impossible that it comes from the other cluster because they don't. The support is not. It's not included in the support of the second cluster.
Perfect. So those components have almost disjoint support essentially.
Yes,
Excellent. Thank you.
Any other questions to Guillaume?
I have a question actually, follow up kind of on Garrett's question. This is Jeff. So if that condition on the separable components and the other assumptions made by Ascalani are not satisfied, I know you mentioned one other result in that direction, but let's say they're not even sort of separable. Do you have an intuition or a guess about the consistency or inconsistency when a prior is placed on the hyperparameter alpha? I'm just curious.
Yes, the intuition comes from the simulation. That's something I went quickly over. So no, I don't have this simulation, but that's something that we explored. We just tried outside of the conditions where, in this simulation setting, the components are not completely separable because you have Gaussian kernels. And the Ascolani and colleagues' results seem to apply, or the behaviors seem to apply. So it seems that it might be possible to relax a bit the assumptions. Maybe not technically, but in practice, yes. I don't have much, further than this. On simulation, we were able to see things that looked reasonable.
Okay, thanks.
Okay, any other questions? Okay, so then let's thank our speaker again, and then thank you everyone. I hope to see you in next webinar.
Thank you.
Thank you, Guillaume. Nice talk. Thanks.
Very much.